So our next section in Chapter 10 is Section 10.3, Hypothesis Tests for a Population Mean, which should feel pretty similar to what we just did in Section 10.2 around a population parameter. Our first objective is to test hypothesis about a mean. To test hypotheses regarding the mean, we need to use the following steps, which are going to come on the next slide. But we first have to make sure that first the sample is obtained using a simple random sampling. We've been doing this for a while now. The sample has no outliers, and the population from which the sample is drawn is normally distributed. And if that's not the case, we have to use a sample size that is large, which means greater than or equal to at least 30 observations per sample size. And the sample values are independent of each other. That is, the sample size is less than 5% of the population size, again, which we've been doing for quite a while. So now let's look at the steps. Okay, for the classical approach, we first are going to determine the null and alternative hypotheses. And of course, these can be structured in one of three ways, either a two-tailed, where the alternative is that it's not equal, the left-tailed, where the alternative hypothesis is it's less than the value given, and then the right-tailed, where the value is greater than the sample given that we're looking at. The second step is to select a value for alpha. Remember, this is the level of significance and connects with sort of our confidence interval about how confident we are of the results of our survey, and that's how you pick the level of significance. Remember, we talked about this in the last section, depending upon the seriousness of making an error. So obviously, we need a higher confidence for more impactful statistical studies. For example, if we're studying maybe things that impact children or medical studies, etc., those are pretty significant if we have errors in them, right? That they could cause some problems. So it's a little counterintuitive because remember that the level of significance, the lower it is, the higher your confidence level. So if you want a 99% confidence level, your level of significance is going to be 1% or 0.01. So a little counterintuitive there, but again, we've been doing this for a while. Then we want to compute the test statistic. Okay, this would follow with the student's t-distribution with n-1 degrees of freedom, and of course we know how to do this with the x-bar minus the x-bar being the sample mean minus the population mean given in a prior study or in a pilot, all over the standard deviation for a sample, lowercase s, divided by the square root of n, the sample size. From that, we use table 7 to determine the critical values. If it's two-tailed, and you can see the diagrams below, if it's two-tailed, we're going to have plus or minus T alpha over 2, right? It's a greater than T alpha over 2 or less than a negative T alpha over 2. The left tail is that the critical values will equal the negative T alpha. And the right tail will, here, we're looking for values to create this critical region. The critical value is just T sub alpha. What we then do is compare the critical value with the test statistic, and we reject the null hypothesis. Basically, all three of these are saying if the test statistic is in the critical regions, then we will reject the null hypothesis. So all of these are just to say, let's just look at the first one, two-tailed. If it's less than negative T alpha over 2 or greater than positive T alpha over 2, recognize that all we're saying in all three of these, if your test statistic is in the critical regions, then you can, that is an implication to reject the null hypothesis. And then, of course, we state the conclusion. This is the classical approach. And now let's look at the p-value approach. Very similar. Step one is the same. Step two is the same. First is identifying your hypotheses, determining a level of significance. Step three is the same too, where we calculate we compute a test statistic. You can see again the formula here. And it's similar again, where what we're doing here is trying to figure out, using that test statistic, to find the critical values. And so p-value equals two times the probability of t being greater than or equal to our test statistic. And we do that because if we just calculate one critical region for a two-tailed system, they're both equal given a normal distribution. If it's left tail, then we're looking for the probability or the p-value in the area left or less than t0. And of course, if it's a right tail, then we're looking for a t-value that's greater than, we're looking for the probability that it's greater than. And then we compare the critical value specifically with the level of significance. And that gives us, if that p-value is less than our alpha value, the p-value that we calculate here for our t sub 0 is less than our alpha or the level of significance, then we would reject the null. And of course, then we state the conclusion. All right. So let's look at a couple examples, or one example, and use both approaches so you can kind of see it walk through. Okay. Again, a kind of a caution. Notice that this procedure requires either that the population from which the sample was drawn be normal, so the whole population is a normal distribution, or that the sample size be large. And again, that means that it's greater than or equal to 30. N is greater than or equal to 30, and that should be a lowercase n, not an uppercase n. And the procedure is robust, so minor departures from normality will not affect the results of the test. However, if the data does include outliers, this procedure should not be used. So when you are evaluating the population the population parameters, and you look at box plots, etc., if there are any outliers, we should not use these methods. Okay. The mean height of American males is 176.3 centimeters. The heights of 44 male U.S. presidents, Washington through Trump, have a mean of 180.1 centimeters and a standard deviation of 7.1 centimeters. Treating the 44 presidents as a simple random sample, determine if there is evidence to suggest that U.S. presidents are taller than the typical American male. And we're going to use the alpha equals 0.05 level of significance, which is a 95% confidence level. So our hypotheses are, we can see it's right-tailed. How do we know that? Because we want to know, where did it say? If the U.S. presidents are taller than the typical. So that means our average given from this, doesn't really say where that comes from. Our average given in there of 176.3, we want to know if the presidents are actually taller than that. And so our alternative hypothesis is that the mean is greater than 176.3. All right, so we can see that it's right-tailed. We have our two hypotheses. The level of significance is given to us in the problem, alpha equals 0.05. And so now we need to calculate the test statistic, okay? So again, we have that test statistic is the average given in our sample, and our sample was the 44 U.S. presidents, and that mean X bar value, 180.1. We're using the population mean given in the problem, which is 176.3. We're using the standard deviation in our sample of 7.1. And of course, there were 44 presidents, so we're using n equals 44. And when we do that, we get our test statistic of 3.550. If we look at table 7, we find our critical value, which is at the alpha level 0.05, and the degree of freedom. Okay, remember the degree of freedom is n minus 1, which would be 43. Okay, this is crossed out. Why is this crossed out? And these are not greater than, but pointing to that we are actually using 40. If you look at table 7, you'll find that, at the higher levels of sampling, we don't have every sample size covered. So it goes by tens at a higher level. And so since we wanted to use 43, we're going to go ahead and use the 40 degrees of freedom to find our critical value for the test statistics. So our T sub alpha, right, our T 0.05 crossed with a degree of freedom of 40. If you look in that table 7, you'll find that value is 1.684. Okay, so if we look in, this is the critical value, so this creates the right tail critical region, all the values that are greater than 1.684, and we shade that area, and so this is the critical region we're going to evaluate against. And so our critical value, where the right tail critical region begins, and our test statistic 3.550, we can see is deep in that critical region. And since the test statistic is in that region, we reject the null hypothesis. And the last thing we do is we create a conclusion statement. And remember, we don't ever really say we reject it. We just say that there is sufficient evidence at the specific level of significance, 0.05, to conclude that U.S. presidents are taller than the typical American male. Okay, so this kind of proved our hypothesis that presidents were were taller than the typical male, and so we're really kind of rejecting the null hypothesis by stating support evidence for the alternative hypothesis. If we do the same exercise with the p-value approach, again, I'm not going to go through step 1, it's the same. Step 2 is the same. Step 3, the first part is the same, where we compute the test statistic, right? The same formula. And now we find the p-value, okay? So we're looking for the probability that the p-value is greater than 3.550. If we look in table 7 again, here we can see that 3.550 is between 3307, that's an entry in the table, and 3551. It's much closer to this second one. We can see that the p-value goes between 0.0005, which would be what is that? 0.05%. So it's between 0.05% and 0.1%. Okay, and we can see this here. So we're looking for the probability that the area shaded to the right, what's the probability of the area shaded to the right that entries will be in there? And so we know that area shaded to the right is between 0.05%, that's not 5%, 0.05%. So 1/20th of 1% to 0.1%, 0.001, and that is 1/10 of a percent. So we state the p-value as a probability, so we have 0.05%. and I used the lower one. And remember, if the p-value is less than alpha, which alpha is 0.05, both of these are both the n values for our p-value are less than 0.05. Okay, so we reject the null hypothesis, and then we state our conclusion. Where is it? There it is. There is sufficient evidence at the 0.05 level of significance to conclude that U.S. presidents are taller than the typical American male. So we have the same conclusion from either method. Okay. Notice these were large sample methods, and we were given an average. It doesn't say where it comes from, but we were given that average. So you kind of have an idea of, hopefully, through these two examples, how they compare and contrast, mainly looking for probability values, in this case the p-value, and then comparing it to alpha, okay, versus in the classical approach, looking to see if the test statistic is within the critical regions. This is just an image of if you had done this exercise using a TI-84 plus. You can see the p-value is 0.0005, 5e to the negative 4, and it also gives you the test statistic 3.550. All right. So again, your calculator can be your friend, or the StatCrunch in the system. So just showing that the technology can handle a lot of these steps as well. So now let's look at an example for testing the hypothesis about a population mean, but using a small sample. And remember, that's if the sample size is less than 30. So here we're talking about the fun size of a Snicker bar is supposed to weigh 20 grams. Because the penalty for selling candy bars under the advertised weight is severe, the manufacturer calibrates the machine so that the weight is 20.1 grams. The quality control engineer at M&M Mars is concerned about the calibration. He obtains a random sample of 11 candy bars, weighs them, and obtains the data in Table 1, down to the right. Should the machine be shut down and calibrated, because shutting down the plant is very expensive, he decides to conduct the test at the 0.01 level of significance. Now, because this is a small sample, we have to first understand if our population is a normal distribution, and which would allow us to use the classical method or the p-value method. And so what we've done here is we just sorry, I went blank there. We have a plot of all the responses. In addition, we also have a box plot. Okay, the correlation between the weights and the expected z-scores is 0.967. If you use a technology solution, you get 0.970. Because 0.967 is greater than 0.923, this is table 6, the critical value for n equals 11. The normal probability plot indicates that the data could come from the population that is approximately normal. Okay. And then we look at the box plot, and there are no outliers. That's another situation where we wouldn't be able to use the normal distribution. So in this case, when we check table 6 and we check the box plot, everything looks good for using a normal distribution methodology. So now we can go back and try our two approaches. Remember, the first step is to determine the hypothesis. And of course, the null is that the average is 20.1 grams, and because we're looking for any difference, okay, we are going to see that our alternate hypothesis is that the mean doesn't equal 20.1. Okay, so this is again another two-tailed hypothesis, and our next point is to select the level of significance. This was given in the problem at 0.01. And so we got some calculations to do. The first thing we want to do is find the average value from the 11 candy bars selected, the average weight, excuse me, and we get the mean of the weight is 20.3. And we want to get the standard deviation for the 11 candy bars, and that equals 0.64. From there, we're going to compute our test statistic, x bar minus our mean, our population mean, all divided by the sample standard deviation divided by the square root of n, which is the number in our sample size. And you see the calculation to the right, and we get 1.042. Now it gets a little, we got some heavy table action coming up, and so I want you to follow along closely with this. First, we find the t-distribution in table 7. We're going to find the critical value that's based on our alpha level, which is 0.01, right? And our degree of freedom, which is 1 less, n minus 1 less than the sample size, so that would be 10. Because this is a two-tailed hypothesis, remember that when we're looking for t-values in our table, we use alpha over 2, t sub alpha over 2. And so what we get for t of sub 0.005 is that those t-values are going to equal 3.169. And remember, these are going to be positive and negative of those t-values. Okay? So we compare the critical values plus or minus 3.169 and the test statistic. And here we can see them, okay? So the values less than the negative t sub alpha over 2, and the values that are positive and greater than the positive t sub alpha over 2 are the two critical regions. And what we're checking is to see if our test sample is inside those critical regions, which it is not. Okay, since the t statistics, the sample statistic, the test statistic is not in the critical region, we do not reject the null hypothesis. And so our conclusion is there's not sufficient evidence to conclude that the Snickers have a mean weight different from 20.1 grams, which means that we do not shut down the machine. The calibration is okay. Okay? So we can do the same calculation, the p-value approach. Of course, step 1, step 2 are the same. Step 3, of course, finding out the mean, the standard deviation. DF stands for degrees of freedom. That's the one less than the sample size. And there's our test statistic. Okay? So again, we have it's the same problem, so it's two-tailed. So now we're looking for the probability in each area below the negative t0 value and above the positive t0 value, and you can see these here. So in order to find the probability using the p-value approach, we need to find the areas in both of these, okay? What we know is that it's symmetrical, so if we find the area in one side, we can just multiply it by 2. So what we're going to do is we're going to find the area of the right critical region, or the right shaded region, and then multiply that by 2. Okay? So our test statistic is 1.042, and if we look at table 7, we can see that the values there are between 0.879 and 1.093. So we know that our t-value is between those 2 points. If you look at the area for the lower value, this area is 0.15, okay? And the area for the upper level is 0.20. Well, remember, we're using a 2 times probability. 2 times the area is based on a symmetrical normal distribution. So we know that the probability value, the p-value, has to be between 2 times 15, which is 0.30, or 2 times 20, which is 0.40. So we know our probability is somewhere in this range. What we're looking for specifically is the probability that's greater than this value, right? 1.0, etc. So we look in table 17 for the p-value where t is greater than 1, and we get that value from table 7. is 17, okay, is 0.17. When we multiply that by 2, we get 0.34. So the probability that we would get the response that we got is pretty good. It's 1 in 3, basically, right? So with the p-values, remember, we compare them to the alpha value, and our p-value, our probability is 0.34, is greater than the p-value. Remember, we reject if it's less than, and so we don't reject the null hypothesis. And once again, we decide that we will not shut down the machine. So our second and last objective in section 10.3 is to understand the difference between a statistical significance and a practical significance. Practical significance refers to the idea that while small differences between the statistic from a sample and a parameter from the population stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. So this is really about a conceptual difference, if you will, or a practical significance. So let's look at an example to demonstrate this. According to the American Community Service survey, the mean travel time to work in Collin County, Texas in 2017 was 29.3 minutes. The Department of Transportation reprogrammed all of the traffic lights in Collin County in an attempt to reduce travel time. To determine if there's evidence that travel time has decreased as a result of the reprogramming, the Department of Transportation obtains a random sample of 2,500 commuters, records their travel time to work, and finds a sample mean of 29.0 minutes with a standard deviation of 8.5 minutes. Does this result suggest that travel time has decreased at the alpha equals 0.05 level? We're just going to use the classical approach. You could also do this with the p-value approach. Either would work. So we have a really large sample, 2,500, so we're not worried about the normal shape. We determine the hypothesis. We're looking as if the time has decreased, so we're looking see if there's a change below the 29.3 minutes of commuting. This level of significance is 0.05, and so our first job is to calculate the test statistic, which we get negative 1.765. Now, if we look at table 7 and find the critical value, with our alpha being 0.05, so that's our t sub alpha, t at 0.05, and our degree of freedom is 2499. Well, when you go to table 7, you'll notice that the table doesn't go up to a degree of freedom of 2499. And so when you are have a sample size or a degree of freedom, so I should say instead, that's greater than 1,000, you simply use the last row in the table. And if we do that, we'll see that for a t sub alpha of 0.05, we get negative 1.645. Now you may see the value in that table is positive, but remember we're doing a left-tailed, and so we're looking for the other end of the normal curve, not the positive end, but the negative end, okay? So finally, what we're going to do is compare our critical value of negative 1.645 and our test statistic of negative 1.765. I don't have a diagram of the normal distribution, but again, remember we're on the left side of the curve, and so we're looking for values that are less than this as far as being in the critical region. Well, negative 1.765 is indeed less than this value, so it will be in the critical region, and therefore we would reject the null hypothesis and make our conclusion that there is sufficient evidence at the alpha equals 0.5 level of significance to conclude that the mean travel time to work has decreased. Okay, so while the difference between 29 and 29.3 minutes is statistically significant, it doesn't have any practical meaning. After all, 0.3 minutes is only 18 seconds. And are you really going to make anyone feel better about his or her commute to work by cutting off, basically 20 seconds? So this is a great example to kind of demonstrate that last point. Okay. Important note is that large sample sizes can lead to statistically significant results, while the difference between the statistic and the parameter is really not enough to be considered practically significant.